So today we are going to continue talking about forces, and just a little heads up, throughout the video you might hear this weird crunching noise, and that's just my dog Bexley chewing on a bone. He's hanging out in the back of the classroom, so don't get too distracted by that. So far we've talked about what a force is and Newton's 3 laws. Hopefully you remember Newton's 3 laws, but just as a recap, the first law is the law of inertia. An object in motion stays at motion with a constant velocity, and an object at rest stays at rest unless acted upon by an outside force. Newton's second law is F equals ma, and Newton's third law is the law that forces always come in pairs. And today we're going to apply those kind of basic force laws and rules to everyday forces that we encounter. And the first one is weight. Now, in one of the earlier videos, we did talk about the difference between mass and weight. The mass of an object is how much stuff is in it, or it's its inertia, how difficult it is to change that object's motion. But the weight of an object is how much gravity affects that mass. So if I am on Earth, my mass is going to be affected more than when I am on the moon, because the gravitational field on the moon is much weaker. So it really depends on where you are relative to other objects. We're going to talk more about what gravity is a little bit later on. So like I said, weight is the force exerted on an object by gravity. When you're close to the surface of the Earth, the gravitational field is pretty constant. It doesn't change a whole lot. And we can solve for weight with this equation. F sub g, which means the force of gravity, is equal to the mass of the object times g. And this g right here is the acceleration due to gravity. And on Earth, it's always negative 9.8 meters per second squared. So if I want to figure out what my weight is in newtons, I would use this equation. I would say force of gravity acting on me, or my weight, is equal to my mass. I don't really know what my mass is, so I'm just going to say 60 kilograms, times the acceleration due to gravity, which is negative 9.8 meters per second squared. And here, I'm assuming I'm on Earth. If I were on a different planet, 9.8 would be a different number. So I would multiply those and find that my weight is about equal to 600 newtons. Hopefully, all of you recognize this equation up here as being Newton's second law. We have a force, and it's equal to a mass times an acceleration. And in this case, the acceleration is the acceleration due to gravity. So what way does gravity act on us? Well, when we draw a free body diagram of weight, we always point weight straight down towards the center of the Earth, or the moon, or Jupiter, or whatever. So we have our object right here. We have a free body diagram, and the force of gravity is pulling down. So that means this is the center of the Earth right here. If our object were somewhere else, if our object were over here, our force vector for gravity still needs to point towards the center of the Earth, so it would be pointing in this direction. It always points toward the center of the Earth. We tend to say down when we are explaining which direction gravity points in, but down really means toward the center of the Earth, and that is more clear than just saying down. So if the object is not on a flat surface, if it's at an incline, the weight vector still points straight down toward the center of the Earth. Just because the object is on an incline doesn't mean that the direction of gravity is going to change. But when we have a plane that is not flat, like this, we want to establish a different XY coordinate axis. It just makes it easier for us in the long run. So we have to decide what we want our new x and y to be. Typically, we think of x and y as being horizontal as x and up and down as y. But this doesn't have to be true. we could change these to point in any direction we want as long as those two lines stay perpendicular to each other. So what we're going to do is we're going to use parallel to the plane as our x here, and we're going to use perpendicular to that, perpendicular to the plane. I'm going to make that in a different color. We're going to make perpendicular to the plane our y. So our x and our y always have to be perpendicular to each other or at a 90-degree angle, but they do not have to point straight up and down and straight side to side. We can tilt them. When we do this, we have to break the weight vector down into components, because now we have our y going this way, and we have our x going this way, and our force of gravity doesn't really match either of those. It's kind of in the middle. So what we need to do is break it down and put it in terms of our new x and y. And the way we do that is using trigonometry. Woohoo! So we have the little black arrow pointing down toward the center of the earth, and that is our force of gravity. And we can use that as the hypotenuse of a triangle. And if we do that, we would have one part of our triangle right here, and another part of our triangle right here. And if you stop and look at this for just a second, you'll notice that one side of this triangle is now on our y-axis, and the other side is now on our x. So we now have our y here and our x here. All we did was we took that force of gravity vector and we broke it down into components. So we broke it down into its y piece and its x piece. And hopefully you guys all remember from math class that in order to find the force of gravity here, we have to use the Pythagorean theorem. And the Pythagorean theorem tells us a squared plus b squared equals c squared. And a squared and b squared are the smaller sides that are at 90 degrees, and c squared is our hypotenuse. So in this case, that is our force of gravity. Our force of gravity is c. So we have c squared is equal to a squared plus b squared. We take the y component of the force vector and the x component of the force vector. So the x component, the y component is right here, and the x component is right here. And we add the squares of those to get the square of the force of gravity. Hopefully that makes sense to you. I know these problems can be quite difficult, so if you have any questions on this, please, please, please ask them next time you come into class so that you can clarify this, because we will do a lot of problem solving using this scenario with an object on an inclined plane. So when we have an object at rest, we know there must be no net forces acting on it, and that is Newton's second law. So if our object at rest is sitting on a table, the force of gravity is still there. It's not like the force of gravity went somewhere else. But if the force of gravity is there and it's not accelerating, what does that mean there also has to be? There has to be a force counteracting gravity. So there is always a force exerted perpendicular to the surface called the normal force, which counteracts gravity. So here we have Lincoln, and he's sitting on a table, and gravity is pulling him down. But he doesn't accelerate toward the center of the earth, so we know there must be another force balancing out gravity so that there is no net force acting on him. And that is the normal force right here. It is only as large as it needs to be to balance the force from the object. So when I put a marble on a table, the normal force is pretty small because the amount of force acting on the mass of that marble isn't very big. But if I put an elephant on the table, the normal force has to be much, much larger to counteract the force of gravity pulling that elephant down toward the center of the earth. And if the force gets too big, then something breaks. And that's when we have like a little picnic table and we put an 18-wheeler truck on it. The mass of that truck is much too large for the table to produce the same normal force pushing back up, so it breaks. So the normal force is a difficult force to understand. It seems really strange that an inanimate object would be pushing on something else. But it happens. It's true. It's pretty much always there. The only time it's not there is when something is not resting on a surface. So if I have a football and it's resting on a table, it's not accelerating down toward the center of the earth, and the normal force of the table is pushing back up on that football. But if I pick the football up and throw it across the room, while it's traveling across the room, there is no surface touching the bottom of that football and keeping it from accelerating down. And in that case, there is no normal force. There is nothing pushing up on that ball to keep it from moving down. And that's why when you throw a football, as it travels, it moves toward the ground. So normal force is a contact force, and it's only present when two objects are in contact. And this force comes about because of Newton's third law. When an object, like this box, is placed on the floor, it pushes on the floor with the force of the object's weight, right? We know that. This box, even though it's not moving, is being pushed down by the force of gravity. But from Newton's third law, we know that if the box pushes on the floor also pushes back up on the box. Remember the picture of the skater from the last video. As the ice skater pushed the wall away, the wall pushed back on the skater. It's the same thing here. The box pushes down on the floor, and in return, the floor pushes up on the box. And that's where the normal force comes from. So how do we work with normal force? Well, recall Newton's second law, F equals ma. What forces are acting on this object and in what direction? Well, if you look at our free body diagram over here, this little dot, we have the force of gravity acting down, and we have a normal force acting up. Those are the two forces we have here. And those forces are the net force. Remember, we can only add forces together if they're in the same axis. So both of these forces are up and down. They're not side to side at all, so we can go ahead and add them together. And we can set them equal to mass times acceleration. This is just using Newton's second law. We have our normal force, which is pointing up, so it's positive. And we have our force of gravity, which is acting down, so it's negative. So we subtract those two and set it equal to the mass of the box times its acceleration. What do we know about these two forces? Well, unless this table or the floor is breaking, whatever this box is on, if it's not breaking, that we know that the force of the normal force and the force of gravity are equal to each other. They have to be equal. And if they're equal, that means these cancel and it goes to 0. So 0 newtons. And if that's true, the other side of this equation also has to be 0. Is it possible that this mass is equal to 0? No, because that would mean that this box doesn't have any stuff in it, that it doesn't have mass. And this box always has mass, no matter where it is. So what must be equal here, then, is the acceleration. And that makes sense. The object is not moving, so acceleration must be equal to 0. So the normal force and gravity are equal to each other. So your homework for tonight is to read this page underneath the video and answer these following questions. Imagine a roller coaster with a loop in it. At the very top of the loop, describe the direction of the rider's velocity, the direction of a rider's acceleration, the direction of the rider's inertia, the free body diagram for a rider, and just a hint, there is normal force somewhere, so you have to have it in there somewhere. And what keeps the rider from falling out besides the straps? So we have the straps keeping the rider in, but there's actually something else going on here that keeps the rider from flying out of the ride. So answer these questions the best you can and turn them in next time you come to class.